Okay, so let's talk about the X-ray tube. It is the part of the equipment. It's what we would consider like the functional part of the equipment, right? Everything else is just to support the X-ray tube so that it can do its job of creating X-rays. First thing we're going to want to know is, for one, we make X-rays with an X-ray tube. So what do we need? Like, what are the minimum requirements to make X-rays? So in order to produce X-rays, X-rays are, by the way, X-rays are a type of electromagnetic wave. Okay? Said in a more simple way, they're a type of light. Okay?
What chapter is the one you're on right now?
Chapter 9, the X-ray tube. So yeah, X-rays are a type of light. If you've been with me for long enough, if you've been with me through physics, you know that light, visible light, X-rays, radio waves, all of that, they come from the movement of electrons. Electrons are the electrically charged particle orbiting around atoms. When they move, when they shake, when they are caused to move fast and then slow down, or if you just were to sit there and shake an electron, again in thought experiment land, shake an electron, it's going to vibrate and wiggle the electric and magnetic field. It's kind of like a buoy in the ocean, right? A buoy moves with the waves in the ocean, right? But you could also take a buoy and move it up and down in the water, and it would create waves in the water, okay? The electron is like the buoy in that case, and the water waves are like the electromagnetic waves, okay? The only difference is the water waves have to move through water, where electromagnetic waves don't need to move through it, don't have to move through a medium. They don't need a medium to move through. They can travel through empty space. Electrons shake, electromagnetic waves happen, okay? So we need a source of electrons, right? The filament wire is our source of electrons. You learned that from the previous stuff on electrodynamics, right? We asked where is the source of electrons in a circuit? It's the wire. The conducting wire is where those electrons come from. You need now a way of accelerating electrons. We said earlier in today's stuff that energy is conserved, right, but can be converted into different forms. One form that energy can take is called kinetic energy. It's the energy of movement. An electron sitting still has a mass, a charge, and a spin, okay? But just consider its mass. An electron sitting still has a mass. It weighs something. You put it on a scale, it has some weight here on Earth. You put it up into outer space, and it has a mass but no weight. But importantly, there is some oomph to an electron. Even if it's a little bit of oomph, it's still there, okay? With the electron accelerating, you now have a massive object moving at some velocity, some speed, okay? A car sitting still has a mass, therefore some energy, but the car has a lot more energy if it's speeding down the freeway, right? It hurts a lot more to get hit by a car at 60 miles an hour than 6 miles an hour, right? So the velocity that matter travels at affects its energy. Okay? Specifically, it affects its kinetic energy, the energy of motion. Electrons moving fast have more energy to give up than electrons moving slowly. We want to make them move fast. So you have to have a way to accelerate electrons. That's the purpose of the high voltage side of the X-ray circuitry. So the purpose of showing you those three parts of the circuit is to tell you, where are we getting the electrons from? It's the filament wire, or the filament circuit. Where are we getting the oomph, the push, to make the electrons move fast so they have a lot of kinetic energy? That's the high voltage circuit. And then you need to run those electrons into something, right? A car moving fast down the road carries a lot of energy. That energy doesn't necessarily do anything, except for move the car down the road, but it doesn't do anything to any object until it hits a wall, for example, right? A car hitting a wall at 6 miles an hour crumples the bumper a little bit, maybe, might make some sound, right? Car hitting a wall at 60 miles an hour crumples a lot more metal, makes a lot more sound, hurts people, damages the wall, right? More energy is deposited into the wall when the car is moving fast at the wall versus when the car is moving slowly towards the wall. In both circumstances, the car weighed the same, has the same mass. The only difference between those two examples is, in the first example, the car is moving 6 miles an hour, slowly, less kinetic energy. And the second example, cars moving faster, 60 miles an hour, more kinetic energy. Okay, so you need a way, if we want to think of the car hitting the wall, think of all of the crumpling of the metal and the sound that you make and the breaking the wall. Think of that as like the work that we wanted to do. Let's say we wanted to make as much sound, bend as much metal, break as much wall as possible. Then you're going to crash the car into the wall a lot faster than if you didn't want to have all that happen, right? Well, we want to use our fast-moving electrons, and we want to take all of their energy away, and we want to use it to make X-rays, okay? That means we have to give them a lot of energy first. Electrons cannot get bigger. You can't give them more mass. What you can do is make them move faster. You can accelerate them. So we need to accelerate electrons and then slam them into a wall so we can use their energy to make X-rays. Go ahead.
Are all electrons the same size?
Yes. Same mass, same charge, and the same spin.
So the only way to upsize that is to have more of them.
More of them, or more of them moving faster. Yes, that's your kV and your mass, or your MA setting, right? More of them or move them faster. Yep. Good, good, good. All right, so in order to do this on the filament side of the circuit, we need to create what's called thermionic emission. Thermionic for heat, and emission for the electrons are being emitted from the wire, okay? Now, normally, when you turn on a light bulb, you see light, right? Well, in this case, this type of light bulb, this filament, may produce some light, but what's important is that electrons moving through the wire, if you try to cram too many of them through the wire at one time, they will not all have a place to sit, okay? If they don't have a place to sit, then they have to move out into the space around the wire. Place to sit is a place inside of an atom, right? If they don't have a place to sit inside of an atom or orbiting an atom, they're going to sit around the wire in the only place that they can, in a cloud around the wire, okay? So by jamming a bunch of electrons, a bunch of current through a tiny wire, you can cause the electrons to move out into the space around the wire. The process is called thermionic emission, and what it creates is something called a space charge, okay? A cloud of electrons in the space around the wire. Electrons are negatively charged, so we have a charged cloud of electrons now. If we set 1 amp or 1,000 milliamps on our machine, how many electrons should be in that cloud? 1 amp. I'm basically asking you how many electrons are in 1 amp.
6.3 billions times billion or something.
Yeah, exactly.
The
You had it exactly right. 6.3 billion times a billion. Billion. Yep. 6.3 times 10 to the 18th. Okay. If you set 1 milliamp, which you can't set that setting, but if you set 1 milliamp, you'd have 6.3 times 10 to the 15th electrons in that cloud. Okay. But if you set a milliamp, or 1 amp, which you're not generally doing a full amp, but if you assume you set a full amp, you'd have 6 billion electrons in your little cloud. Okay. And any fraction of that is also true, right? But that's an easy example. Okay, so during this whole time, by the way, how did you create the space charge? You pressed the prep button, okay? The same button that spins the rotor, makes all the noise, also charges the cloud around the filament. This is on the negative side of the X-ray tube called the cathode side, which we're going to look at big picture stuff in a second. Here's the idea. Electrons are running through that wire, hopping off of the wire. During this whole time, there's an equilibrium. Some electrons are hopping back onto the wire, while others are hopping off, but it maintains a net amount of electrons in this cloud so that we can use them. So the filament wire is where they came from. Once we put enough current through the filament wire, the electrons boil off the wire into a little, almost like a gaseous type cloud. Okay. Now, you've got your cloud of electrons. What are you going to do with it, right? So now comes your exposure. The exposure button activates the high voltage circuit. What kind of circuit, is it AC or DC current for high voltage? DC, direct current traveling in one direction across the X-ray tube, right? So once you press the exposure button, that cloud of electrons is repelled from the negative side that it came from, because like charges repel, and it's also at the same time attracted to the positive charge. It's pushed and pulled away from where it came from across a small gap, okay? We use voltages measured in tens of thousands, and with that much voltage, we can make electrons move extremely fast, something close to about half the speed of light. And I don't know if you know much about light speed, but we don't move anywhere close to that, even with our fastest anything that we have, okay? But electrons moving through a circuit at extremely high voltage can move very fast. 50% of C or more. C is the speed of light. The space between cathode and anode face is about 1 inch. So these electrons jump about a 1 inch gap in a tiny fraction of a second. Okay. Remember from a few lectures ago where we said in a circuit electrons only move about 1 inch in an hour, right? Well, in this split second they're going to move a full inch. That's because they're not moving through a wire over this split second. They're actually jumping a gap in space from the filament wire cloud to the face of that spinning disk. They're arcing from one side to the next.
Do they lose any energy in that arc?
Ooh, that's a good question. So if there was matter between the filament and the face of the anode, if they ran into anything, they would lose energy. But one important part of the X-ray tube is that the X-ray tube is a vacuum. It's empty. So nearly no energy loss. Now, if it were much longer, then if that gap were much bigger, then we might see an effect. But with the gap very small, there's near to no energy loss there. That's a really good question.
How small is the gap?
About an inch, a centimeter or two, something like that, yeah. It's really, I mean, you can look up inside of an X-ray tube and you can sometimes see that gap if the tube is positioned right. But yeah, it's not very far. It's macroscopic though. It's a big distance for the electrons to travel, but for you, it's that far. Okay, so here's the deal. Those electrons are at the same time pushed and pulled across that gap at a high rate of speed. Depending on the voltage, they move faster or slower. Okay, and then they collide with the anode disk. This disk is called an anode, positive end. They collide with that disk. The disk is special. It's made out of an element called tungsten or molybdenum or a combination of those things. Anyways, the point is that the material is an extremely dense material, okay? If you crashed a car into a wall of cardboard boxes, it's going to go right through the wall of cardboard boxes, right? But if you crash a car into a concrete wall, like a reinforced concrete wall, it's going to stop at the wall, right? You will take more energy away from the car when you crash it into a brick wall than a wall of cardboard boxes, right? The car's just going to blow right through the cardboard box wall, taking away less of its energy. So you want a material that is going to stop the electrons, has a high atomic number. The electrons are suddenly and dramatically, bless you, decelerated. They're bless you again. They are slowed or stopped, okay? Once the electrons have hit the anode disk and are stopped, we don't care about them anymore. Because after they're stopped, they have produced X-rays, okay? When they stop, when you take and move, they're moving at a high rate of speed across a gap in space, and they hit the anode disk, and they individually interact with the atoms of the anode disk, they emit X-rays from that, a bunch of other stuff too, but they emit X-rays. All of their kinetic energy is taken away, and then those electrons just work their way back into the circuitry, and we don't care about them anymore, okay? After they've interacted with the anode, collided with the anode, they've let all their energy out, and we've now used it to do something with. The law of conservation of energy, as we've been talking about, says, for example, kinetic energy lost from decelerating electrons is converted into other forms. The forms that it's converted into happen to be electromagnetic waves, light. Some of it is visible light. If this were clear, if the X-ray tube had a clear casing around it, you would see some light emitted when you made your exposure, okay? You would also feel some heat from the exposure, and some of it would be the X-rays that you cannot see or feel, okay? You're sensitive to electromagnetic waves, just not all of them, right? You cannot see or feel radio waves, but you can but you can feel thermal waves, right? You can feel infrared, it's heat, okay? You can't feel visible light, but you can see it, okay? And you can neither feel nor see X-rays, okay? So the type of electromagnetic wave that it is will you will sometimes be able to detect it, like you can see visible light, okay? It's the same type of thing as an X-ray, it's just different in its energy. X-rays are more energetic. We don't have any evolutionary advantage to have a sensory receptor for X-rays, so we don't have any ability to sense them. Can't see them, can't feel them, can't smell them, right? But visible light we can. Radio waves we can pick up with our car's antennas, so depending on like our equipment, we can detect or use these waves in different ways. You know, Wi-Fi, your cell phone signals all work on radio wave principles, okay? They're sensitive to the radio waves. Anyways, the point is that there's a law in nature called the law of conservation of energy, and it just says take a system where something's happening, you put energy into it, you're going to get the same amount of energy out, but the energy out's going to come out in different forms, okay, than it went in as, or it may come out in different forms. Okay. But either way, the energy is conserved. Total energy in equals total energy out. Electromagnetic waves coming from the anode, this is sort of the same thing I just said, include not only X-rays, also infrared, heat, ultraviolet, the stuff that gives you sunburns, and visible light. Again, the anode disk glows, lights up during the exposure. There's a good reason for that we may not have a chance to get to today. That's X-ray production, which is chapter 10. I don't know that I'm going to make it there. Here's a bummer thing. The efficiency is extremely low. Less than 1% of the total energy used to make the exposure actually makes X-rays, okay? Almost all of the energy goes to visible light, radio waves, and infrared, okay? Most of the energy is wasted. Still equal energy in equals energy out, but most of it is waste energy. That's why after a long day, you'll find your X-ray tubes are very hot. Okay, they heat up, and actually sometimes we can use them so much that they heat up too hot, and we have to consider stopping using them for some time, allowing the X-ray tubes to cool. Okay,
They heat up really fast.
They do heat up very fast. You know, even before you make an exposure on a patient for the day, you have to warm up the X-ray tube because they produce so much heat that if you start off a cold unit and make a high-level exposure, you can actually warp the components. You can vaporize parts of the anode disc, you can crack it, you can crack the glass, you can bend and warp the bearings that support this anode. The bearings heat up. You can hear these bearings, right? These are old, used up bearings making lots of noise. Does anybody have an X-ray machine that sounds like that when you turn it on? Sounds like bearings rubbing together. Some do, some don't, right? And you might notice that if yours doesn't, it might start to make some louder noises towards the end of the day. As it gets hotter and hotter and hotter, everything kind of gets a little looser, making more noise. You'll notice that this anode disc, I'll pass this around in just a second. Quick note here, when you hold this disc, hold it from the actual rotor shank. Do not grab the bottom here. There is a ring around the bottom where the broken glass was. I did my best to remove all of it, but there's still a little bit of residual stuff, so hold from the rotor shank like that. But I'll pass this around so you guys can see this. Notice the cracks in it, notice the pitting in here. All of that is coming from the, you can grab the rotor face too, like the actual disc too, just don't grab the bottom. All of that has come from the long time use of this equipment, and sometimes it's just normal wear and tear, but other times it's improper use because of the amounts of heat we're making. You know, if you look back to this first couple of notes here, we're creating 3,700 degrees Fahrenheit of temperature in the electron cloud, okay? All of that is going to the anode disk and heating up the disk. Alright, so X-rays come out of the anode disk after we smash electrons into it. So one more time, what are the three things we need to make X-rays? What's one of them?
Energy power.
So we need something. So let's start with Lewis. We need a source of electrons, right? What's the source of electrons? Good, filament wire. What do we, now we've got a cloud of electrons around the filament wire, that's our source. What are we going to do with them?
Accelerate them.
What do we accelerate them with? Like, what does that? Voltage, which does the push and pull. We call that an electromotive force, EMF, okay? Now that you have fast-moving electrons moving half the speed of light across a gap, what's going to happen to them?
They need to decelerate them.
They need to decelerate, right? When they're moving fast, what kind of energy do they have? Kinetic energy. When they decelerate, you are removing or converting, we could say like an individual electron, we can say it is losing kinetic energy as it decelerates, right? But we know that energy is not lost, it's converted. So kinetic energy is converted into what type of energy when they decelerate? Joe, what's up?
Electromagnetic.
Electromagnetic energy. What's an example of electromagnetic energy? It's one example. X-rays? Ultraviolet. What's another good example? We have Emmanuel. Good, okay. Anything else? So we have X-rays, ultraviolet. Lewis told us X-rays and ultraviolet. Anything else coming out of the X-ray tube that's electromagnetic energy? Infrared, visible light. All of those types of light waves are created when the electrons hit the anode disk, okay? Of the total 100% of that energy going in, how much of it is converted into actual X-rays? Less than 1%. The book says 0.5, right? Different authors might say slightly different things. Some authors say 0.1, some say just less than 1, others say 0.5, it doesn't matter. Anything less than 1% is what we're talking about. The other way to think about it is almost all of the energy goes into making other types of other forms of energy. It's because it's easier to make those lower forms of energy. It's hard to make X-rays, so X-rays are a small chunk of the energy we convert. Okay, good. Let's get into our X-ray tube component.